All right. Morning, everybody. Thank you for coming back. I know that you've obviously been busy getting ready for the test, but now that's in the rear view mirror. I'm probably somewhere between a third and halfway done grading the midterm. You should have grades up certainly by tomorrow, probably by sometime this afternoon. My guess with this first exam, the first exam is typically, I think for a lot of people, maybe the darkest part of the class. Like it's sort of the hardest part of the class. We've kind of been learning these new skills at a pretty rapid pace, and this was our first chance to really test ourselves. And I think that what happens is as the ball starts rolling, we start to see how all these thermal problems are end up being kind of the same or a similar problem. So try not to be too discouraged if you found it challenging. I think it's normal for the first exam to be challenging. Remember that the way this class is structured is that I'm more concerned with how you do at the end of week 10 than how you've done, in whatever we are in week 4. So your final exam can overwrite one of your midterms. So even if you didn't get the result that you were hoping for, it's still possible for the final to overwrite that grade. The other thing that I think I would say is if you don't know what to do, try to trust the process, right? We're going to talk about how the process is going to be, we're going to try to look at it so the way to solve all these problems is the same. And you'll see that in this lecture too. So try to fall back on that process, right? Write down the governing equations, write down your assumptions, demonstrate that you understand this process. And I think that then I can help you as I'm grading because you're demonstrating that you understand what to do, even if you get tripped up at some point along the way. Right? So we've been talking in the last couple of lectures about open systems, right? And that's going to be the focus of the next exam, right? And for open systems, we have to first draw control volumes, then perform conservation of mass. And once we figure out what the mass is doing, then we can use that information to find out what's going on with the energy. Right? So we talked about conservation of mass. Basically, the dm by dt is equal to the sum of the mass flow rates in, minus the sum of the mass flow rates out. We talked about steady state and how that dm by dt term would go away if we're under steady state conditions. Then, last class and the class before, we started to talk about conservation of energy. Now, this is more complicated than the first law for closed systems, because the first law for second systems, we have to take into account the energy that's coming in and out with the mass. And also in open systems, we're typically interested in what's going on in a snapshot, right, at any given instant in the problem, instead of an elapsed time version of a problem. So here we have a rate equation, just like we did for conservation of mass, versus the elapsed time version, which we were using on the first exam. Right, so those are kind of the differences. The other big difference here is that with open systems, we'll sometimes have to deal with kinetic and potential energy, right? And those terms can cause us trouble even in metric units. But when we deal with English units, it gets even worse, right? These imperial units are always harder. We have to divide by GC if one of those terms survives. And then we'll probably end up converting from foot-pounds to BTU, which means we would divide by 778 as well. So I'm trying to teach you a way to look at all these problems as being the same, right? So the first question that we have is the system open or closed, right? And if it's closed, then the version of the first law that we use is dE by dt, or is delta E is equal to Q minus W. We make some assumptions, and we get that delta U is equal to Q minus W. We find work as the integral of PdV. We find delta U as the mass times the change in the specific internal energy. And then we've got to ask, what's the fluid? And knowing what the fluid is, whether it's water, if it's water, we need to know what the phase is, right? And if it's air or some other ideal gas, we have to know whether it's constant specific heat or variable specific heat, right? Now, what's going to happen is if it's open, right, our flow chart gets bigger. It's got a whole other branch to it now because the system could be open. first we have to figure out what happens to the mass. Now, this was a trivial thing for closed systems because what happened to the mass was nothing, right? So now we have to do this dm by dt is equal to the sum of mass flow rates in minus the sum of mass flow rates out. Then we'll ask what happens to the energy, right? dE by dt is equal to q dot minus w dot plus the sum of m dot in, h in plus v in squared over 2 plus gz minus the same thing for the mass that's going out. But now the problem becomes kind of the same. Now the paths start to branch back together, right? Right? Although for open systems, we usually won't find Q and W, or Q dot and W dot in this case. We don't have a nice expression for open systems like W is equal to the integral of PdV. Instead, in the first law, we'll often have to think about, we'll use our engineering intuition, right, about these different components and say, oh, that component is a turbine, and turbines generate power. So I'm going to assume that the power term is much, much bigger than the heat transfer term. So I'm just going to cross the heat transfer term out, right? Unless I'm told the heat loss from the turbine. And then after that, I've got to say, what's the fluid, right? And that's the same question I was asking for open systems, but now I ask it to find the specific enthalpy, right? Which remember is U plus PV, instead of the specific internal energy, right? But it's the same thing. Is it water or something like it? And if it is, where are we on a PV diagram? Are we a subcooled liquid? Are we a two-phase mixture? Or are we a superheated vapor? And if it's an ideal gas, then I got to solve the problem either by using variable specific heat, which for air would mean using table A22, or for constant specific heat, which means that we would use now Cp times delta T to find H. Remember, the U looks kind of like a V, so Cv times delta T to find the change in specific internal energy. Enthalpy, right, has a P in it, right? So now we want Cp times delta T to get the change in H if we're using constant specific heat, right? So this, in a nutshell, right? And I know it's much harder than this because every problem's got its own wrinkles, like how do you find certain things? How do you fix certain states, right? But this is kind of our big flowchart for how to do single systems or single process problems in thermodynamics, right? And it's certainly not trivial, but if we think about it in this framework, it takes away some of the difficulties of trying to plot the path, right? So remember, we're doing this, and pretty soon we're going to get to the point where, you know, now we're understanding how to use individual processes, right? We're going to put them together to make different things, right? So it's nice, we just finished the exam. Let's step back and see what we're going to try to do, right? So we need to know what happens to the mass, right? So for some of these, we treat, even though it's not true all of the time for the whole cycle of an internal combustion engine, we'll treat internal combustion engines as closed systems, right? A series of processes in a closed system, right? And we'll treat the rest of these things like airplanes and nuclear plants and air conditioners, we'll treat them as open systems. So we'll use the open version of the first law. What's the fluid, right? So for internal combustion engines and jet planes, we'll say that the fluid is air or something like it, some kind of ideal gas. And for air conditioners and refrigerators, which use refrigerant, and coal and nuclear power plants, which use water, right? In both of those cases, we're bouncing back and forth across the vapor dome. So those are kind of similar based on what the fluid is, right? And then what's the point, right? We'll see when we start to talk about these different cycles. We'll have to characterize, colloquially, we like to use this word efficiency as kind of a synonym for like goodness, like how good is something? Oh, it's efficient, it must be good, right? But the word efficiency in thermodynamics has a couple of different very specific meanings, and we'll get into that. But some of them will define how well we generate power, right? So remember, thermodynamics is we're taking heat energy, we're burning something to create, that generates heat, and then we use that heat to make power, right? So how much of that heat did we turn into work, right? And we'll be able to define an efficiency that way. If my air conditioner broke last summer, right? Obviously in the hottest week of the summer, because that's when air conditioners break, right? But when we were, shopping for a new air conditioner, right, it talked about a SEER rating, right? And that's kind of like an efficiency, or tells you, what you do with an air conditioner is that you put in mechanical work and you transfer heat in a direction that's not the direction that heat normally wants to travel. That's why we can cool our house in the summertime, right? Even though in a normal universe, heat would be coming in from the outside into your cold house, right? But we're trying to keep the house cold, right? So we have a way of defining something that's kind of like an efficiency for air conditioners. And again, commercially, we talk about SEER ratings, which are kind of the same thing as what we'll talk about, which is coefficient of performance, right? So there's different ways to think about these different cycles, right? We call them a cycle because they start and end in the same point, right? So we have a bunch of different processes, right? But we start and end in the same point, and that means we can go around and around and around for basically ever, right? That's kind of the plan with something like a nuclear plant, is that you sort of turn it on and then it just keeps running, right? Until it's time to decommission it, right? And obviously there's, different engineering challenges for decommissioning something like a nuclear plant, right? So today we're going to focus back in on some of these open system problems, right? So we're going to look at two different types of components, right? So the first is a pump, which I'll go through in the slides. And then when we talk about heat exchangers, because there's different ways to kind of slice up or do the analysis on a heat exchanger. So I'll do that in Word, right? So the first thing that I want to look at is a pump, right? So this pump, it tells us a given pressure, a pressure coming in, right, at 0.1 megapascals or 100 kilopascals. It tells us that this is saturated liquid water, right, so that its quality is 0. So it would be all the properties like UF or VF, right? And it gives us a mass flow rate in kilograms per minute. If this was right at the beginning of the problem, maybe I'd turn that to kilograms per second, right? And then all it tells us about the outlet is that the pressure goes from 0.1 megapascals to 0.6 megapascals. Now, what a pump does, it's the opposite of a turbine. What a turbine does is it takes the enthalpy from the fluid and turns it into mechanical work, right, or power. A pump does the opposite. A pump adds mechanical work into the system to increase the enthalpy of the system. Now, remember, enthalpy is U, specific internal energy, plus PV, right? Pressure times the specific volume. So the way that we're increasing the enthalpy in this case is that we're increasing the pressure from 100 kilopascals or 0.1 megapascals to 600 kilopascals or 0.6 megapascals, right? So by spinning these fan blades, we're increasing the pressure in the system. So how do we solve this problem, right? There's two things that we can do first. My goal is usually to try to do the symbolic solution first, because I think that's more similar problem to problem, and it kind of demonstrates my understanding. But eventually we're going to have to fix the states, right? So here, when I start to fix these states, I see that one of these states I know two things about, right? I have two independent intensive properties. So I know I can fix state 1. State 2, I actually know that I can't fix because I only have the pressure, right? And then if I wanted a process table, I could track the heat transfer and the power for this process. So where do we draw the control volume, right? So here, we just draw this dotted line, right? So it follows the wall on the inside of this pump, right? Except for it runs perpendicular to the inlet and perpendicular to the outlet. That's my control volume. Conservation of mass is the next thing on my list. And it's fairly straightforward because this process is, we're going to assume that it's at steady state. So because it's at steady state, we can get rid of this dm by dt term. But the other cool thing about this pump, right, that's going to make our lives easier, is that it only has one inlet and one outlet, right? So then my summation signs are going to go away as well. So conservation of mass in this case is not as trivial as a closed system where it's just the mass always stays the same. But it's not too bad here because there's one inlet and one outlet. So that means there's only one mass flow rate in the problem, right? So my continuity equation, my conservation of mass equation up here, tells me that m dot in minus m dot out is equal to 0, or that m dot 1 is equal to m dot 2. So I'm just going to lose the subscript, and I'm only going to call it the mass flow rate. So there's only one mass flow rate, and it's 10 kilograms per minute. Now we start to move to conservation of energy. Now we can't have different assumptions for conservation of mass and conservation of energy because they're in the same problem, right? So the system's still at steady state. It's still got one inlet and one outlet. But because this is a pump, right? Well, first, I guess we're going to say that this change in elevation is pretty small, right? So that the change in the potential energy is close enough to 0, right? Especially since we don't even know what that height is, but maybe it's on the order of like, I don't know, a foot or something, right? So not that big, right? And then we're also going to assume that the change in velocity doesn't really matter here, right? The change in the kinetic energy. We know from conservation of mass that if the area at the inlet and the outlet were the same, then the velocities would be actually the same. And we showed before, when we worked on the turbine problem, that the kinetic energy, because it's in metric, and it ends up being in joules per second, if we were talking about meters per second, we have to divide by 1,000. It ended up, at least in that turbine problem, it was pretty small, right? Like fractions of a percent. So here we're going to assume that it's not that important either, right? Now, the other thing, because I'm not told what the heat loss from this pump is, I'm going to assume that it's much smaller than the power that's going in, right? So I'm going to basically assume that the heat transfer rate here is 0, right? That even if the system is not perfectly insulated, that term is small enough that if I just assume it's 0, the power that I get won't be much different from what actually happens, right? So now I've started with my sort of fundamental equation. I've made my assumptions, and I get this expression that hopefully we're going to eventually start to expect from things like pumps and turbines, right? And remember, I made that little Disney joke last time, right? Because we're looking for work or power, right? And the dwarves work really hard, so this is hi ho, H in minus H out. And then we let our hip to win sign convention figure out the signs, right? We let the first law deal with the signs. And in this case, because it's a pump, right, we expect that work is going into the pump. So work in is negative. We expect this value to be negative. So now we've used the first law and we've got a symbolic solution. That's great, right? But let's say it's an exam and Dr. Scherzer is actually asking me for a number, right? So I'm going to have to do some math here to figure out the number, which means I got to fix the state, right? And I only have enough information to fix state 1, right? When I look at this expression, I don't have the power. That's the thing I'm trying to find. I do have the mass flow rate. I don't have H1 and I don't have H2, right? So how do we find H1 and H2, right? They're both subcooled liquids. So if I knew the temperatures, I could say like HF at a given temperature, right? But I don't know the temperature, I don't think. Let's see what we know, right? So what's the substance? The substance is water, and we know that it's liquid on both sides. Or somebody didn't, manufacture the pump very well. If you have boiling that's happening in a pump, what happens is you have these little water bubbles or steam bubbles, right? And they'll impact on that impeller, and it'll wear down your system over time, right? So for the pump, right, we know that for the first state that quality is equal to 0, right? So at 0.1 megapascals, 100 kilopascals, we know that we're at quality equal to 0, right? We know that's about 100 degrees. If you don't know that off the top of your head, that's fine. You can find it in the table. Then the other thing we know is that the exit pressure of the pump is 600 kilopascals or 0.6 megapascals. But I can't fix the state with just that information, right? So there's a little bit of trickery that goes on in these pumps, right? So this is another thing that's a problem, right? Because maybe that first law part is going to be common for most of the problems that we do. We'll just make different assumptions. But then every little problem has its own, every component can have its own divergent path of how you fix the state, right? And these pumps are a little bit tricky, right? So I could fix state 1 here, right? I could come in and I could find H1, right, for 1 bar, and it's 417.4 kilojoules per kilogram. So I could find H1, right? And if I had H2, right, so H1, the temperature here is right around 100 degrees. And if I had T2, then I could find H2 as well. I could say, well, H2 is going to be about equal to HF at T2. But I don't know T2, right? I only know the pressure. Right? So I could find the specific volume. It's about 1 over 1,000. Always, the specific volume for liquid water is always about 1 over 1,000. And I know H1. But I can't find H2 because I only know the pressure. Right? So the other thing that I know here, sometimes if you only know one piece of information about a state, you got to ask yourself, what's the process? Right? How do I get from state 1 to state 2? Sometimes it's an ideal gas and you can use PV is equal to MRT, right? Sometimes when it's a closed system, you have a pressure volume relationship and that'll help you fix the state, right? But in this case, we know that it's a pump, right? But I don't know T2, so I can't solve the problem yet. So I'm going to assume that the pump is ideal, right? Now, in real life, nothing is ideal, right? We'll learn about why perpetual motion machines can't work in the universe that we live in, right? But not till next class, right? So for right now, I'm going to tell you that ideal pumps are pumps where there is no pressure change, right? So I'm going to assume that in the best case, the least amount of power that I would have to put into this system would be the case where the pressure doesn't, or where the temperature doesn't change across the pump, right? So now we have this alternate method that we're going to use for ideal pumps. This is going to be an important thing for us to remember. So again, this is another thing. If we see pumps, again, we should have this spidey sense kind of thing that happens where we say, oh, there's a trick to this. Right? I got to remember the trick, right? So here I'm going to remember the definition of specific enthalpy, and that's specific internal energy plus pressure times specific volume, right? So here I could rewrite my equation, m dot times H1 minus H2 as m dot times U1 plus P1 V1 minus U2 minus P2 V2, right? And then I start to say, well, if I assume that the temperature at the inlet and the outlet are the same, and that U, right, the specific internal energy is only a function of temperature, right? Then I can say that I can get rid of this delta U, right? Now, we might say, well, Dr. Schertzer, you told me before that I could approximate H for a subcooled liquid as only HF of T as well, right? But if we did that, we would find that the pump requires 0 power to work, right? Now that doesn't work, right? So if I bought a pump from Home Depot and I put it in my garage, I have to plug it in to make it work, right? So something is going on. There has to be a delta H here. So we can't use that first approximation, but we can use it to get rid of the specific internal energy. Because what the pump really does is it elevates the pressure of that fluid as it moves through the system, right? So we're going to assume that because in this ideal pump, the temperature is the same, we're going to assume that the specific volumes are the same, and we're going to assume that the specific internal energies are the same. So if I do that, right, if I make this delta U 0, then I get this equation, m dot times P1 V1 minus P2 V2. This only works for ideal pumps, right? Then if I also say, well, it's water and the temperature's about the same, so the specific volumes are about the same, then there's no difference between V1 and V2. It's just V, right? So then this is going to be mass flow rate times the specific volume times P1 minus P2. So this is where you don't necessarily need to know the derivation, how we got here, right? But you do want to know if you get an ideal pump, this is the equation that you'll end up using to find delta H, right? So right now we have, how do we find delta H? And we talk about, water, it's a subcooled liquid, or it's a two-phase mixture, or it's a superheated vapor. We're going to have to add, to that list now. Sure, it's water, but is it going through an ideal pump? Because if it's going through an ideal pump, then I can approximate delta H as the specific volume times the change in pressure. Right? So we're going to use that for these ideal pumps. And then we can put some numbers in here, right? So now I know the pressure difference. I don't know V2, but I'm assuming, because I'm also assuming that the temperature is about the same, I'm going to assume that the specific volumes are about the same too, right? About 1/1000. So now I can put that in here, right? I got to remember that this was H in minus H out, so it filters down to be P in minus P out, or instead of dealing with megapascals, I like to put this in kilopascals because then I'll get an answer in kilojoules. 0.1 megapascals is 100 kilopascals minus 600 kilopascals, right? About divided by 1,000 when I put the specific volume in here, multiplied by 10 kilograms per minute, right? And I'm going to get this weird unit, right? So here I'm going to make some unit conversion stuff, right? And this is going to be kilojoules per minute, and I can turn this into, or kilojoules per second, I can turn this into kilowatts, right? So this pump requires almost negative 0.1 kilowatts, right? Now, you're never going to go to Home Depot and ask for a pump. Probably you'd convert this to horsepower if you were going to Home Depot or Walmart or something to buy a pump, right? You're never going to ask for a pump that has a power of negative 0.1 kilowatts, right? Or whatever the horsepower equivalent is. The sign there is to tell us, engineers who understand what's going on with the first law, that the pump is consuming power. It's not delivering power like a turbine would, right? So here we started with conservation of mass, right? We made some assumptions. We saw that the m dots were equal, right? Then we went to conservation of energy, and we saw that W dot was equal to m dot times H in minus H out. Then we assumed it was an ideal pump. And because it was an ideal pump, that delta H became specific volume times the change in pressure, right? And here we get the sign that we expect. So that's how we deal with pumps. I'm going to take a little bit of time. I won't solve this numerically, this next part. We'll just do it symbolically, because here, this is R134A, which is the type of refrigerant. It's a refrigerant that replaced Freon. So if you were around in the area, or maybe your parents were around in the 80s, or even maybe the 90s, we were using Freon. Then we moved to this R134A, and it's now been replaced by Preon, I think is the name of the new refrigerant. So that's kind of another thing that was no fun about replacing my air conditioner, was that it really was just leaking refrigerant. But in order for them to seal the leak and then pull out the old refrigerant, like they can't actually get the old refrigerant because it was this R134A, this in-between refrigerant that they're actually not making anymore because environmental regulations are phasing it out. Right, so we're given some information here, right? And what we're asked to do, right, is we don't have to worry about is the process possible yet. We don't know how to do this yet, right? But when we're asked to, maybe we want to find out how much heat is being transferred from the air to the refrigerant, right? So the refrigerant comes in at, some higher temperature, right? And it's cooled off by the air, right? Or actually the air is cooling down, so the refrigerant is heating up, right? So this would be your air conditioner. It's pulling in air from your house, right? It takes the air in the house, and maybe it's at 32 degrees Celsius. That's pretty hot. Hopefully your house isn't that hot, right? And it's pushing it out at 22 degrees Celsius, right? And then it's doing that by boiling the refrigerant on the inside, right? So we won't fix the states, but we'll try to figure out how much heat is being transferred in between these two things, right? Or how do we do a first law analysis on a heat exchanger like this? Now remember, we talked about this. This is a shell and tube heat exchanger because there's a tube here that runs through a shell. Now we use this when we have two different fluids that we can't mix, right? So we have the refrigerant stays in its tube and the air flows over it and heat transfers through the wall of that tube. So our first question is, where are we going to draw our control volume, right? So now my first option is I'm going to draw the control volume around the whole heat exchanger. So when I do this, it means that I have both the refrigerant and the air in my system, right? So I'm going to write out the first law, right? It kind of takes a little while, but get used to doing this. dE by dt is equal to Q dot minus W dot plus the sum of M dot in, H in plus V in squared over, I think that this is in metric, but let's pretend it's in imperial. Because if it was in imperial units, then I would say divided by GC plus G over GC times Z in minus the sum of M dot out, H out, plus V out squared over 2 GC plus G over GC Z out. Right? So now, right, so I'm assuming this is an open system, right, because mass is coming in and out. So that gives me this equation, right? So now the assumptions that I'm going to make for this system are that it's at steady state. I can't say that it's one inlet and one outlet, so I can't get rid of those summation signs, but there's no fan blades anywhere inside my heat exchanger. So I'm going to assume that the power is 0, that this is passive. I'm not plugging it in, and it's not delivering power. I'm going to assume, even though I went through all the trouble of drawing my GCs, I'm going to assume that delta KE is 0, right? And delta PE is also 0. And here's the weird part. I'm going to assume that this is adiabatic. This is weird, right? Because it's a heat exchanger. Its whole purpose in life is to transfer heat. So how the heck can it be adiabatic, right? So what does this assumption actually mean, right? Now, remember, when I'm talking about Q dot and W dot, Q dot is the heat transfer that passes over the boundary of my control volume. So what I'm assuming here is that even though heat transfer is happening inside my system, that I have insulated the heck out of this heat exchanger. That there is heat being transferred from the air to the refrigerant, but none of that heat gets transferred to the outside. None of that heat goes to the surroundings. All of the heat lost from the air gets accepted by the refrigerant. So that's what this assumption means. So this means all heat lost from air goes to the refrigerant. Now, I could make this problem harder by saying that, 10% of the heat lost from the air goes to the refrigerant or something like that, right? And then we would have to have a number here. But what I'm going to say is that this is adiabatic, right? So now I'm going to fill this out, right? I'm going to say that 0 is equal to, Q dot goes away, M dot goes away, the sum of M dot in H in minus the sum of m dot out H out. At this point in the problem, you know what I just realized? We forgot to do conservation of mass, right? Because one of the important things we have to do for this problem is conservation of mass. And it's not going to be as straightforward as that pump was, right? So I know conservation of mass is dm by dt is equal to the sum of m dot in minus the sum of m dot out. But this is not a simple control volume. There's two inlets and two outlets, right? So we know that we're still at steady state. So this goes away, right? But there's two inlets and two outlets, right? What this says is 0 is equal to the mass flow rate at state 1. I'm going to call state 1 is where the air is coming in. So I'm going to call this air in plus the mass flow rate. So I need the other inlet is the refrigerant inlet here at state 3. M dot of the refrigerant inlet minus m dot of the air out minus m dot of the refrigerant out. Now, can any of the refrigerant come out where the air is coming out? What do you think? You can just give me a thumbs up or a thumbs down. Can any of this refrigerant come out in the same place that the air comes out? No, right? Because what happens is the refrigerant's all in this tube, right? So the refrigerant that goes in at state 3 has to come out at state 4. So I can look at this, provided that my thing's not broken, right? I guess if I leave this in service long enough, maybe it rusts and you get a hole and refrigerant starts to leak or something, right? So what I know here, I can collect the terms here. This is going to be m dot air in minus m dot air out plus m dot refrigerant in minus m dot refrigerant out. And what I can see from this, right, because the air and the refrigerant can't mix, right? This means that I really only have two mass flow rates here. So I have in here, I have the mass flow rate of the refrigerant, and over here, I have the mass flow rate of the air, right? So this equation doesn't tell me that explicitly, but if I look at this as an engineer and I think about it, then I can see that there's really only two mass flow rates in this problem. So as I put this information back up into my first law, I can group these not by inlet and outlet, but I'm going to group them by air and by refrigerant. So here, this is going to tell me that 0 is equal to m dot m dot of air. Now the air inlet is going to be here at state 1, H1, and the air outlet here is going to be at state 2, H2, right? This is minus because this air outlet here comes from this term minus m dot air out times H air out, right? And similarly, I can say m dot times of the refrigerant times H3 minus H4. So what does this tell me, right? Nothing yet, right? But what this is going to do is it's going to say that m dot air, I'm going to flip this over to the other side, H2 minus H1 is equal to m dot, well, why don't I do this? I'll keep this as out minus in, right? This is H out minus H in. And I'll call this negative m dot of the refrigerant H out, H4 minus H3. Right, this is also H out minus H in. So this is what the first law tells me. Physically, what does this mean? If, well, let's do the next part first, okay, right? And we'll come back to this and we'll talk about what physically this means in just a second. Because I could also look at this system. Let's say, let's just do the refrigerant side, right? So now I'm going to draw my control volume here, right? And it's going to now have this heat transfer is coming from the air into the refrigerant, right? So now if I do my first I'll do conservation of mass, dm by dt is equal to the sum of m dot in minus the sum of m dot out. I know the system is at steady state. Now in this case, there is only one inlet and one outlet. This tells us what we already knew before, right? But before we had to use some intuition to figure this out. M dot, 3 is equal to m dot 4, right? The refrigerant, and I'm just going to call that the mass flow rate of the refrigerant, right? Now, when I go to the first law, dE by dt is equal to q dot minus w dot plus the sum of m dot in h in. I'm still going to pretend this is an imperial, right? V in squared over 2gc plus g over gc, c in, minus the sum of m dot out, h out, plus v out squared over 2gc plus g over gc z out. Now, I make almost all the same assumptions, but not quite, right? I've already said that this is at steady state and that it's got one inlet and one outlet, right? We're going to neglect the kinetic and potential energy changes. We're still going to say that it's passive. But now, there is a heat transfer term that comes across my boundary, right? So in some ways, this is easier because it's one inlet and one outlet. In other ways, it's harder because it's got this heat transfer term that goes across the boundary. So now we're going to say Q into the refrigerant is equal to, let's not skip that step. So this is going to be 0 is equal to Q dot plus M dot of the refrigerant, right? This is the same mass flow rate times H in, which is state 3, minus H out, which is state 4. But what I actually want to solve for here is Q dot R. So Q dot R is going to be equal to M dot of the refrigerant. Now I got to make this H out minus H in, H4 minus H3. So when I'm trying to find heat transfer rates, remember when we were trying to find power, it was high-ho. When we're trying to find heat transfer, it's ho-high. Now, I don't think they made that Disney movie yet where somebody's singing that, but it's just the opposite of work, right? So now what this means is that if I'm trying to find the heat that goes into this refrigerant, it's going to be M dot R times H4 minus H3, right? So I could also do this on the air side. I'm going to do this really quickly, and I'm just going to sort of jump to the answer. So from conservation of energy, or from conservation of mass, right? Just like the refrigerant, we're going to find that m dot air is equal to m dot 1, which is equal to m dot 2, right? We're going to do this. The analysis here is going to be the same. Steady state, one inlet, one outlet. There's only one airflow rate, right? So now I guess this would be like the, this green control volume over here. Now my conservation of energy is going to be the same too, except I'm going to get from energy, I'm also going to get 0 is equal to Q dot, but now it's of the air plus M dot air H1 minus H2, right? Or Q dot air is equal to M dot air H2 minus H1, right? H out minus H in. So if I was trying to find the heat transfer of the refrigerant, I'd use this equation. The heat transfer of the air, I'm going to use this equation. And here's the cool thing. When I went up and I did, right? So remember, so Q dots, heat transfer rates are going to be m dot times H out minus H in. When I looked at the whole system, what happened in the whole system was that m dot air times H out minus H in was equal to negative m dot R H out minus H in, right? So what this tells me, physically, what this means is that this is Q dot air is equal to negative Q dot of the refrigerant. Another way of thinking about this is that the magnitude of Q dot air is equal to the magnitude of Q dot refrigerant, right? But the signs are different, right? Because the air is hot and the refrigerant is cold, so heat is going out of the air. Heat out, right? Heat in is positive, so heat out is negative, right? So I expect this to be a negative number, right? Or let's do this, right? I expect this to be a negative number, right? But the refrigerant, heat's coming into the refrigerant, right? Heat in is positive. So I expect the heat transfer rate for the refrigerant to be positive. So what this tells me when I did the first law analysis on the whole system, it tells me, oh, the heat transfer, all the heat that left the air, where did it go? It went into the refrigerant. And the reason that we got that answer is because we assumed that the system was adiabatic, right? What that means is that the heat exchanger was perfectly insulated. So none of the heat from the air was lost to the environment. So the only other place it could go is into the refrigerant, right? And that's what this answer told us, right? Was that all the heat that's lost from the air goes into the refrigerant. If you want to know the refrigerant heat transfer, find the air heat transfer and multiply by -1. So that is all that I wanted to show you today, but I'm happy to stick around if people have questions, right? Now the thing, I guess the take-home message here from the heat exchangers is you got to think about what piece of information that you want and what control volume to draw. So typically, this equation is good if you want a mass flow rate. If you're trying to, let's say you know how much heat was lost by the air, but you don't know the mass flow rate of the refrigerant, right? If you know one of these mass flow rates but not the other, and you can fix all the states, then you can draw your control volume around the whole heat exchanger, and you can find a mass flow rate, right? But if what you want to know is how much heat is lost by the air, doing a control volume on the whole system doesn't really help you, at least not directly. You might be able to use your intuition to figure it out, right? So if I want how much heat is lost by the air or gained by the refrigerant, let's say, because we did that one more explicitly. If I want to find out how much heat is gained by the refrigerant, then I draw my control volume only around the refrigerant. Because when I do that, this heat transfer term is going to survive. So I'm going to be able to solve for that heat transfer term, right? So oftentimes, you'll end up using both of these things. Because maybe on one side of your heat exchanger, you'll know everything, right? Or you'll be able to find everything. And then on the other side of the heat exchanger, maybe you know everything but a mass flow rate, right? So this is when I was in Toronto, I did some consulting work for a company that was themselves consulting for Ontario Power Generation, who runs the nuclear power plants just outside of Toronto. And the way that they keep them cold, right, is that it abuts Lake Ontario, right, just like us, which is a huge thermal reservoir, right? So you ever go swimming and you notice that once you go a certain depth, it's like there's a clean line and the temperature below that line is very cold, right? So what they do is they take water from Lake Ontario from below that line where it's about 4 degrees, and they pump it in, and they use that to cool some heat exchangers that are running in that power plant, right? But there are some environmental regulations that say, oh, you can pull that water out at 4 degrees, but there's some maximum temperature where you can put it back in, because otherwise, you'll promote algae growth, which is kind of a big problem in the Great Lakes these days, or maybe you'll kill fish, right, or other wildlife, right? So there's different environmental regulations. So one way that you can, right? So here we can see, it's going to accept the same amount of heat, right? And because of environmental regulations and the environment, I'm fixed at what the enthalpy is going in and going out. So the thing that I can throttle, the lever I can pull, is how fast the mass goes. So if the mass goes through my heat exchanger faster, then it will have a smaller temperature difference. Right, so we're over time now, but I will stick around if people have questions.
Thank you.
You're welcome. Have a good weekend, everybody.
Thank you.
Remember, we have a break next week, so we're back on Friday.
Thank you.
Thank you. Have a good weekend. See you next Friday.